Welcome to This Explainer. Today, we're diving into a story that absolutely shocked the math world. We're going to look at how an AI cracked an 80-year-old geometric cold case. And get this, it did it by using completely the wrong kind of math. So, how exactly does an AI solve an 80-year-old geometry problem using the wrong math? Well, that's the mystery we're unraveling right now. What we're looking at today isn't just a computer crunching numbers faster than a human. No, this represents a massive qualitative leap in AI. We're talking about a machine demonstrating genuine intuition, crossing the boundaries between totally different academic disciplines, and kind of fundamentally reshaping our entire understanding of what artificial reasoning can actually achieve. Section 1. The 80-year math mystery. To really appreciate the magnitude of this breakthrough, we need to travel all the way back to 1946. That's when legendary mathematician Paul Erdős posed a question. It's known as the planar unit distance problem, and the premise is deceptively simple, which is exactly why mathematicians love geometry, right? Just imagine you have a completely flat piece of paper and you draw a certain number of dots on it. Let's just call that number n. The big question is, what's the absolute maximum number of pairs of those dots that can be exactly a distance of 1 unit apart? It sounds like a fun little game of connecting the dots, but scaling this up to infinitely many points, the math becomes staggeringly complex. Erdős actually ended up offering a cash prize out of his own pocket for anyone who could solve it. For almost 8 decades, the smartest human experts in combinatorial geometry were pretty confident they knew the shape of the answer. Based on Erdős's own early work using a square grid pattern, the dominant belief was that the optimal answer grew at a very specific rate, roughly n to the power of 1 plus a tiny shrinking fraction. But the AI, it completely shattered that long-held assumption. It proved the number of pairs actually grows way faster, establishing a strict new bound of n to the power of 1 plus delta, where delta is a fixed positive number. So long story short, human intuition was just plain wrong. Section 2. The unexpected AI detective. Because what's truly astonishing here isn't just the final solution, but the actual detective who solved it. We're talking about an internal, general-purpose reasoning model from OpenAI. And this is a super crucial point. This was not some highly specialized, narrow math bot programmed specifically to crack geometry. Not at all. It was a general-purpose model. It was handed a collection of unsolved Erdős problems just to see, if advanced AI could actually contribute to frontier scientific research. No handholding. It was just given the problem statement and basically set loose. The approach it took was just fascinating. Instead of looking at 80 years of human belief and trying to prove that the expected answer was right, the AI showed what OpenAI calls deep mathematical intuition. Its internal chain of thought revealed that it economously decided to hunt down a counterexample. It literally realized all on its own that the human assumption might be flawed and went looking for the crack in the foundation. Section 3. Crossing the math divide. To understand how the AI succeeded where human geniuses hit a wall for 80 years, we really have to look at the tools it decided to pick up. So human experts spent decades attacking this using combinatorial geometry, right? That was considered the correct way to do it. But the AI completely crossed the math divide. It reached into an entirely different branch of mathematics, algebraic number theory. It used incredibly deep orthodox tools, things like infinite class field towers and Golod-Shafarevich theory. Now, don't worry if those sound like a foreign language. The main takeaway is that they belong to a completely different universe of math. The AI used them to pick a geometric lock. Noga Alon, a world-leading expert, even noted that humans simply hadn't thought to use these sophisticated algebraic tools for an elementary geometric question. The AI spotted a connection that humans were just completely blind to. What's super cool about this is how it highlights a whole new era of human-AI collaboration. The AI proved that the exponent, delta, was strictly greater than 0, but its initial proof didn't spit out an exact number. However, using the AI's brand new number-theoretic bridge, Princeton professor Will Sawin was able to take that proof and actually refine the exact mathematical exponent down to 0.014. It's like the AI laid the tracks, and the human helped drive the train perfectly into the station. Section 4. Winning over the skeptics. Solving the math, that might have actually been the easy part. The real challenge was winning over a community of highly skeptical human judges who, frankly, had been burned before. We have to remember the context here. Just a few months prior, in late 2025, there was a huge false alarm. A claim went around that an AI had solved 10 Erdős problems. Turns out, the model had just hallucinated and basically regurgitated existing solutions from the internet. Yeah, pretty embarrassing. So for this May 2026 breakthrough, rigorous independent verification by external human experts wasn't just a polite formality. It was absolutely vital to prove this wasn't just another clever trick of pattern matching. But this time, the proof held up. It was airtight. In fact, it drew a stunning endorsement from Tim Gowers. He's a Fields medalist, which is essentially the Nobel Prize of mathematics. He said that if a human had submitted this paper to the most prestigious math journal in the world, he would have recommended acceptance without any hesitation. He even called it a milestone in AI mathematics. So the AI finally met the absolute strictest, most elite standards of human peer review. And what makes this even more compelling is the reaction from Thomas Bloom. Bloom was actually the most prominent vocal critic of OpenAI during that 2025 false alarm. But after reviewing this proof, the biggest skeptic turned into a believer. He fully endorsed the result, pointing out how it shows unexpectedly deep layers of number theory. I love how he phrased it. He said, AI is now helping us more fully explore the cathedral of mathematics we've built over the centuries. Section 5. A new era of AI. Let's take a step back and look at the big picture here, because we're really not talking about AI as just a smart calculator anymore. This is exactly why this breakthrough is a true qualitative leap. The AI autonomously solved an open, 80-year-old conjecture in an active area of research. It didn't just spit out training data, it constructed an original, massive, multi-step logical argument. And mathematics is the ultimate testbed for reasoning, right? Every single step has to be totally flawless. By finding this really non-obvious bridge between algebraic number theory and combinatorial geometry without relying on simple pattern matching, this general-purpose model proved it has evolved from a simple assistant into a genuine frontier researcher. Which leaves us with this final thought to take away from our explainer today. Think about this. If a general-purpose AI, one that wasn't even explicitly trained for this task, can possess the intuition to bridge massive academic disciplines and crack an 80-year-old cold case, what limits are truly left on its ability to reason? What other mysteries of the universe is it going to unlock next? Thank you so much for joining me for this explainer. I really hope this sparks as much curiosity for you as it did for me.